Hello everyone, my talk today is titled Measurement of Diboson WZ Production Cross-Section with the Atlas Detector. That's basically what I did as a master's student. Here's my outline of my talk. My talk is going to divide it in four parts. The first part is a motivation of Diboson WZ analysis. In this part, I'm going to tell you why we want to do the WZ analysis and why this is important and interesting. And then I'm going to give you a short introduction to the HC and Atlas, which is the accelerator and the detectors, which we acquire data for our analysis. The following two parts is the major part of my talk, and also is my major contributions. These are WZ cross-section measurement and the boosted decision tree. And then is the conclusion. Alright, first the motivation. Motivation here is why we want to do WZ analysis, why this is interesting. If you look at the three Feynman diagrams, these are WZ productions in standard model theory. The last diagram, which included WWZ vertex, this is the triple gauge coupling vertex. This vertex is important because it's very sensitive to new physics. Any detections about the deviation between the standard model and the new physics will originate from this vertex. So this is important. And also, the S channel is the only channel which can give you this vertex, make this WZ analysis very unique. So first, the WZ analysis is WZ event is observed by Fermilab in US. It's the CDF published in 2007. But so far, we don't know much about WZ because the Tabletron, which is the CDF located on this accelerator Tabletron, has not enough statistics. The energy, the colliding energy is not enough for us to detect the WZ events with enough statistics. So here, if you look at the bottom right plot, you see the black dot line with the error bars is the real data of WZ signal. You see, these suffered very much by the statistical error. So that's why we want to do it in LHC with much larger collider energies and much more luminosities. Here is the table I'm going to show you the comparison between the Tabletron and the LHC, the WZ productions. If you look at the figure in the red frame, the third column is the square center of mass equals to 1.76 TeV, which is the Tabletron colliding energy. It's about 10 times less than the LHC, which are on the fourth column. So LHC gives us a unique opportunity to detect WZ with enough statistics again. So this is very interesting to detect this in LHC. So what we do here is the ZW decay to lepton channel. Here the lepton is just electron and muon, not included tau, because tau will decay and make things very complicated. So we just use the leptonic decay, the electron and muon channel, because it's clean and it's ambiguous. But if you look at the particle data group, the book, you will see that the ZW decay to jet has much larger branching fractions, about at least 10 times larger. Why we don't use ZW to decay to jet? Because it's difficult to distinguish between the ZW to W jets, because every time you include jets, it will cause problem, because jets is just complicated to separate and reconstruction. So we don't want that trouble. We just use the leptonic decay, and it's clean, and it's ambiguous. So here I listed the major backgrounds for our analysis produced on LHC. That's ZZ, decay to full lepton, the TD bar, the Z gamma, the Drell-Yan, the Z jets, and WW. If you look at the second column, is the cross-section for these backgrounds. Most of the backgrounds has larger Some backgrounds have even orders higher than the signal productions, so that makes things even difficult to distinguish this very sensitive signal from these huge backgrounds. So that's why we want to introduce both the decision tree method, which is a advanced statistical method, the multivariate method to do this analysis, because it's for traditional method it's just not very effective to select this kind of sensitive signals. So the following several slides I will show you the Feynman diagrams of all the backgrounds. I'm going to show you why these backgrounds will fake our signal. The first is the ZZ background, because ZZ, the Feynman diagram is only U channel, T channel, because S channel is just prohibited in standard model. So if one of the lepton just failed to be detected by our detector, so that becomes the 3 leptons, and if you can fake a missing ET, they will become our signal, because you know it's a hadronic collider. The missing ET is everywhere, so this will definitely fit to our signals. And the second one is the TT bar. The TT bar background is the final state. They include 2 same flavored leptons. This pair of leptons, if this one fall into a Z mass window, they will fake a Z, and the jet will produce lepton signals. Definitely, there's no problem for jet to produce this kind of signal. So TT bar again is our major background. The Z gamma, here I show you the 2 plots, 2 Feynman diagrams here. The first one is the initial state radiation, the final state radiation. These two, both our signals, both our backgrounds. I'm sorry. If the missing ET and the third lepton has been fixed, they will become our signal. And again, the Brillouin, the pretty similar mechanism. And last is the Z jet. Here Z is the real Z compared to our signal is the real Z, but the jet can fake the third lepton and also the missing ET fake, so they will become our background. Alright, that's all for our backgrounds. Then I will give you a short introduction about the LHC and Atlas. Here, LHC is a large hadron collider. It's built in CERN and 100 meter underground on the border of Switzerland and France. Here the circle is about 47 kilometers, and they will accelerate the proton, 2 proton beam to 7 TeV, then make the center mass to 14 TeV collision, and the luminosity will be reached 10 to the power of 34, which is very large. And they will start to take data at the end of this year. So all the analysis in my talk, in my master's, is based on the Monte Carlo data. It's not a real data, because there's no real data now. Colliding data, I mean. And just on the LHC, they're located at Atlas. Atlas is the very large detector. If you look at the figures of the dimension, it's 44 meters long, 25 meters high, and they got very complicated sub-detectors. The very inner one is the tracking detector. The yellow one, the dark yellow, is the electromagnetic calorimeters, and the greener still in the barrel part is the hadronic calorimeters, and the most outer parts, the blue region covered the most outer region, is the muon spectrometer. I have been honored to be involved in the commissioning of the end-cap muon spectrometers at CERN from 2006 to 2007, and it's a pretty impressive experience.